Scientists uncover clues that could make Mach-10 flight possible. A major step forward in understanding how air behaves at extreme speeds may bring hypersonic flight, travel at more than 5 times the speed of sound, much closer to reality. New experiments suggest that air turbulence at Mach 6 acts far more like slow-moving air than scientists once thought. If this trend holds true, engineers may be able to design hypersonic aircraft without completely reinventing the rules of aerodynamics. If you like my content and want to listen more interesting science stories like this, then subscribe my channel. And don't forget to like and share this video with your friends and colleagues. Why hypersonic flight matters. Hypersonic aircraft could shrink the planet in a literal sense. A route like Sydney to Los Angeles, normally a 15-hour ordeal, could potentially be reduced to a single hour. For comparison, Mach 1 is around 760 miles per hour. Reaching Mach 10 would push an aircraft towards 6,600 miles per hour. Professor Nicholas Parzali, a fluid mechanics researcher who recently earned the Presidential Early Career Award for scientists and engineers, focuses on making this future possible. He notes, "It will make travel faster, easier, and more enjoyable." The scientific challenge: turbulence and heat. Flying this fast creates intense heating and violent, chaotic airflow. Unlike slow-moving air, where density barely changes, air at hypersonic speeds becomes compressible. In simple terms, the air gets squeezed, which affects pressure, temperature, lift, and drag. This makes designing a Mach 10 aircraft enormously complicated. For decades, one idea has helped scientists navigate this complexity: Markovin's hypothesis. Proposed in the mid-1900s, Markovin suggested that even though air compresses and heats up at high speeds, the pattern of turbulence itself remains surprisingly similar to turbulence at lower speeds. If true, this would mean engineers could rely on existing knowledge of low-speed turbulence when building hypersonic vehicles. The problem? Until now, no one had strong experimental evidence to confirm or reject the hypothesis. A breakthrough built on lasers and krypton gas. Parzali's team took on this challenge. After 11 years of development, they created a unique experiment. They filled a wind tunnel with a small amount of krypton gas. A laser pulse ionized the krypton, forming a perfectly straight glowing line. High-speed cameras watched how the line bent and rippled as the air rushed past at Mach 6. The distortions in that glowing line acted like a tracer, revealing the structure of turbulence inside the flow. The results were striking. Turbulence at Mach 6 looked much more like slow-moving turbulence than expected. This offers tangible support for Markovin's hypothesis. Funding for this work came from the Air Force Office of Scientific Research and the Office of Naval Research. Why this matters for future aircraft? Designing a hypersonic aircraft requires powerful supercomputers. Simulating every tiny detail of Mach 6 airflow is so demanding that even the world's best computers struggle. But if turbulence behaves similarly across low and high speeds, engineers can make simplifying assumptions, reducing the computational workload dramatically. This could accelerate the design of hypersonic passenger aircraft, high-speed military vehicles, and reusable launch systems for space access. Parzali notes that future hypersonic craft might even reach low Earth orbit without rockets, making spaceflight cheaper and more routine. A small step toward a faster future. Although the new study does not fully prove Markovin's hypothesis, it provides some of the strongest evidence yet. Each experiment narrows the uncertainty and brings engineers closer to designing aircraft capable of surviving and operating at Mach 10. For now, hypersonic travel remains a scientific challenge, but with breakthroughs like this, the idea of crossing the planet in an hour is no longer just science fiction. It is becoming a problem scientists can realistically solve.